In the last lecture, we discussed some of the thermodynamic properties of an ideal gas, like internal energy, entropy, specific heat capacity at constant volume. Today, before discussing pressure function, here we will see that in the last video we basically took V by N equal to KT upon P, and many students asked how. So it is very simple. We know ideal gas equation PV is equal to nRT. Okay, from this relation we can write V is equal to nRT upon P. This is equation second. But we know that this nR is basically equal to the total number of atoms or molecules into Boltzmann's constant. So if we introduce in place of nR, we get this relation nKT upon P. So this will be equation third, but here V is divided by total number of atoms or molecules, so it will be simple. V by N will be simply equal to nKT upon Np. Simply this and N will cancel, is equal to KT upon P. Or you can say if N is equal to 1, that means the number of moles is equal to 1. In that case also N will be equal to Avogadro's number. How? Because the number of moles is basically equal to N upon Avogadro's number. This is equal to 1, so N will be equal to N. So this was very simple substitution there. Okay, one more equation we expanded in the last video. This equation, the entropy one, entropy is equal to nR ln e raised power 5 2 plus ln of 2 pi m kt upon h square to the power 3 by 2. In place of n by v, we introduce it simply value of upon p. Okay. This can be written as nr. We will simply say this ln and e will go, and it will be simply 5 by 2 plus. So what we do here, we will give this ln back to these terms. It will be raised power 3 by 2. So it will be simply log m into n type or log m by n. So it will be plus then ln of k power 3 by 2 plus ln of t raised to the power 3 by 2, and this will be minus ln of h. 2 and 2 will cancel, it will be h cube. And Here this is multiply to the ln, so it can be written as plus ln of k plus ln of p minus ln of. So this is how this equation is expanded. So here you can see this is log m raised power n. This is also that type, and we will actually write these terms, the same terms, at one place. So we will get this equation: s is equal to nr 5 by 2. This can be written as 3 by 2 because this will be log m raised power n ln of 2 pi m plus 3 by 2 ln of k. This term here, one more term is here, so we will write plus ln of k. Again, this is 3 by 2 ln of t, so here one more t is here, so we will write plus ln of t. Okay. Then minus ln of p, and it is simply, you can write it as minus 3 times ln of h. So it is very simple. This will be 5 by 2, this will be also 5 by 2. Now 3 by 2 plus 1. Okay. So this will be equal to nr 5 by 2 plus 3 by 2 ln of 2 pi m. Or you can separate this term also. It can be 3 by 2 ln of 2 pi and 3 by 2 ln of m plus. Okay. So it will be 5 by 2 ln of k plus 5 by 2 ln of t minus ln of p minus 3 times ln of h. So this way we expanded basically the last equation. Okay, in today's topic we will see how this pressure is related to gas constant and volume. First we will write the pressure in terms of partition function. Pressure is basically equal to nRT dou ln of Q dou V at constant temperature. Remember, we are actually deriving these equations for a monoatomic gas. So for the monoatomic gas, this partition function will be simply translational partition function. So we can introduce the value here: nRT dou by dou V of ln of 2 pi m kt upon h square whole power 3 by 2 into volume, and it is at constant temperature. So if you look carefully, this differential of ln of this much, or we can separate this, we can write it as nRT dou by dou V of ln of 2 pi m kt upon h square 3 by 2 plus nRT, we are giving this term back, and differential also back. It is very simple. So it will be ln of V then. So obviously this term, constants are involved here, so this will be equal to 0. So we are left with this term. That means it will be equal to nRT. It will be simply differential of ln of E with respect to V. It will be 1 by V. You can simply write it as nRT upon V. Okay. So you can say this is basically the equation of state for n moles of an ideal gas. Now enthalpy we know is related by H is equal to U plus PV. So we will simply introduce the value of internal energy for a monoatomic gas, that is equal to 3 by 2 nRT. This we have already derived, plus in pressure we have derived here. So we will write in place of pressure this term. This is basically pressure. So we will write nRT upon V, and it is multiplied by this V, so it will be here. So it is very simple now. This V and V will cancel, so it will be equal to, this is 3 by 2 times nRT, it is 1 times nRT, so it will be equal to 5 by 2 nRT. So this is the enthalpy for a monoatomic gas. Okay. Sometimes a very simple question is asked. Question is calculate the constant volume heat capacity of an ideal but monoatomic gas. This is very simple. What you have to do, you know this CV for a monoatomic gas is simply related by this expression. So we will simply introduce the values of gas constant, that means the 3.14 joule per mole per Kelvin. So this will be simply equal to 12.47 joule per Kelvin per mole. So this is very simple question. So now we will move towards the work function. Now this work function A in terms of partition function is equal to minus nRT ln of Q upon N plus 1. So here Q is equal to simply the translational partition function for a monoatomic gas, 2 pi m kT upon h square raised power 3 by 2 into volume, and simply we will introduce one more term, that means PV is equal to nRT, or we already know this is equal to nRT upon P, or we can write it as NK P upon P. So we will take these pointers into consideration, and first we do here, we will simply expand this, it will be minus nRT. It is ln of m by n. So first what we will write this 1 plus it will be ln of q minus ln of n. Okay, so in place of q we will introduce the value of this partition function, and in place of v what we introduce, we will introduce this value. So a will be equal to minus nRT 1 plus ln of 2 pi m kt upon h square raised power 3 by 2, and in place of volume we will simply write nkt upon p. Okay, and minus this ln n. So this will be our equation. Now we will simplify this or expand this little more. So a will be equal to minus nRT, 1 will be here, so it will be 1 plus. So you know now how to expand this, so we will simply introduce the values of here. So it will be, if I take first to the h, so I can write it here, it will be minus, I am simply giving this ln back to these terms, so it is ln of h cube, okay, plus 3 by 2 ln of 2 pi m plus 3 by 2 ln of k plus 3 by 2 ln of t plus ln of m plus ln of k plus ln of t minus ln of p and minus ln of n. So this plus and minus ln it will go, so we are left with our work function. We write it as minus nRT 1 minus, you can write it as 3 times ln of h cube, or write it as such, ln of h cube plus 3 by 2 ln of 2 pi m plus 5 by 2 ln of k plus 5 by 2 ln of t minus ln of p. So this is the expression for the work function for a monoatomic gas. Okay, now we will take now the Gibbs free energy here. Gibbs free energy, you know, in terms of partition function, G is related by this expression minus nRT ln of Q partition function upon A. Okay, so we will simply introduce, we have already done this ln of Q upon N, so we will simply write the value here. It will be minus ln of h cube plus 3 by 2 ln of 2 pi m plus pi by 2 ln of k plus pi by 2 ln of t minus ln of t. Okay, so this is how the Gibbs free energy can be written in this form. Okay, thank you.